Hello students. So today we are going to discuss the sixth topic of your syllabus, that is work, energy and power. Work, energy and power. In our previous topic we have studied about the force. Okay, so this is the further part of the mechanics. Okay, and here what it mean by work? What it mean by work or work done? Okay, in your day-to-day life, you may use this word in many times, in many cases. But in physics, its meaning is restricted to a particular parameter or for a particular quantity. So ನಾವೇನಂತೀವ ನಂದು ವರ್ಕ್ ಅದ, ನಂದು ರೈಟಿಂಗ್ ವರ್ಕ್ ಅದ, ಓಕೆ, ನಂದು ಟೀಚಿಂಗ್ ಮಾಡೋ ವರ್ಕ್ ಅದ. ಓಕೆ, ಸೊ ಈ ಥರ ವರ್ಕ್ ಅಂದರೆ ಅದನ್ನ ಬೇರೆ ಮೀನಿಂಗೇ ಬರ್ತದೆ ಆ್ಯಸ್ ಅ ಗ್ರಾಮರ್. But in physics, the work means there must be the two parameters. There must be the two quantities. One is the force and the other one is displacement. So whenever the body is displaced, as an action of the force, whenever the body is displaced as an action of force, then we call it as a work. And you say there is work done. There is work done. For example, so this is a surface and we keep a body on this surface. Okay, somehow we have applied a force in this direction. So this is applied force. So that applied force is neither along x axis nor along the y axis, is in between those two. Okay, and we know this, this is F, and we know the force is a vector quantity. This is a vector quantity. We have to resolve it into two components. So this is the y component, so which can be written as Fy. Okay, and here this is the Fx. And this is the angle theta. Then I can write Fx equal to F into. So here if I take a triangle, this becomes the adjacent side. So the side which is at the adjacent, so the value which is at adjacent side, that will be associated with the cos function, that will be F into cos theta, is it? And here obviously this will be F into sin theta. Okay, and as a result of this force, if the body is displaced, so from here to here the body is displaced, I call this is the displacement d. So then the product of, so work done is the product of the component of the force, along the direction of displacement. So there are two components, Fx and Fy. So which component should I take? So I should take the component which is in the direction of the displacement. ಡಿಸ್ಪ್ಲೇಸ್ಮೆಂಟ್ ಯಾವ ಡೈರೆಕ್ಷನ್ದಾಗ ಇರ್ತದನೋ ಆ ಡೈರೆಕ್ಷನ್ದಾಗ ಇರೋ ಕಂಪೋನೆಂಟನ್ನು ಅಷ್ಟೇ ತಗೋಬೇಕ್ರಿ. ಸೊ ಬಿಕಾಸ್ ಆಫ್ ದಿಸ್ ಕಂಪೋನೆಂಟ್ ಆಫ್ ಫೋರ್ಸ್ ದ್ಯಾಟ್ ಬಾಡಿ ಇಸ್ ಡಿಸ್ಪ್ಲೇಸಿಂಗ್, ನಾಟ್ ಬೈ ದ ದಿಸ್ ಫೋರ್ಸ್. ಈ ಕಂಪೋನೆಂಟಿಂದ ಅಲ್ಲಿ ಡಿಸ್ಪ್ಲೇಸ್ ಆಗ್ಲತ್ತಿಲ್ಲ, ಈ ಕಂಪೋನೆಂಟಿಂದ ಡಿಸ್ಪ್ಲೇಸ್ಮೆಂಟ್ ಆಗ್ಲತ್ತದ. ಸೊ ಐ ಶುಡ್ ಟೇಕ್ ದ ಕಂಪೋನೆಂಟ್ ಆಫ್ ಫೋರ್ಸ್ ಇನ್ ದ ಡೈರೆಕ್ಷನ್ ಆಫ್ ಡಿಸ್ಪ್ಲೇಸ್ಮೆಂಟ್ into the displacement. So that will give you the important quantity called the work. Or I can write it as W is equal to F into D into cos theta. This becomes the formula for the work done. If the entire force is along the direction of the displacement only, so then the theta becomes 0. Then we can write only Fd like this, is it? And next one was a SI unit of work. SI unit of work. This is okay. So for the force this is Newton, and for a distance it is meter. So if you write like separate like a Newton meter, so Newton meter become the unit. But the SI system, in SI system we write the joule. Joule is a SI unit of work done. So joule means Newton meter. So actually it's a name of scientist. To honor that scientist, I have given the name of that scientist to this unit. Okay, and the symbol is a capital J. Okay, many times I have explained you, while you are writing the unit completely, you should start with the small letter, and if you want to write it symbolically, you should mention the capital letter. Okay, so this is SI unit. What about the dimension formula? Dimension formula for the work done. So for the force, M L T to the power minus 2, and for the displacement there is one more L. So finally this is M L square T to the power minus 2. This is a dimension formula for the work done. Okay, next work done may be 0, work done may be 0, or that may be positive or negative also. Okay, see here, so when the work done may be 0, when the work done may be 0, so there are some cases. Okay, if there is a displacement, without the action of force, if there is a displacement without the net force, then we call, if there is no force, okay, then the work done is 0. Okay, if there is a force, I call a finite force, and there is no displacement, then also the work done is 0. And we are having some special cases, even though there is a force on a body and there is a displacement as a result of the force, but still we can get the 0 work done. So that is because of this one, theta. Suppose the entire force is in this direction and the movement is here, then what do you say? So the angle between those two is 90 degree. Then I can write, if theta is equal to 90 degree, then the work done is 0, even though there is a finite value of displacement and the finite value of the force. Is it? Okay, in all three cases we can get the 0 work done. Okay, you may ask me the examples, like when the work done is 0, or when there is a displacement without the net force. Suppose the body is moving in uniform motion. Suppose the body is in uniform motion andre enagtadare, the body have to move with the uniform velocity. If the body is moving with uniform velocity, its acceleration is 0. If its acceleration is 0, m into acceleration, its force will be 0, right? If its force is 0, then the work done is 0. It means if the body is moving with a uniform velocity, then we say there is no work done. Okay, and what is the example for the second case? If there is a force and there is no displacement, for example, I am applying a force here, I am applying a lot of force on this wall. So is there any work done? Even though I may consume some amount of energy from my body, na iವಾಗ ಏನು ಮಾಡ್ತೇನೆ ಇದನ್ನ ಹಿಂಗೆ ಪ್ರೆಸ್ ಮಾಡ್ಲಾಕ ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತಾನೆ. ಇಟ್ ಮೀನ್ಸ್ ಐ ಆಮ್ ಅಪ್ಲೈಯಿಂಗ್ ಸಮ್ ಫೋರ್ಸ್. ನಾ ಎಷ್ಟೊತ್ತು ಮಾಡ್ಬೋದು, 5 ನಿಮಿಷ, 10 ನಿಮಿಷ, 1 hour ಮಾಡ್ದೆ, ಐ ಗೆಟ್ ಟಯರ್ಡ್. ಸೊ ಬಿಕಾಸ್ ಆಫ್ ದ ಕನ್ಸ್ಯೂಮ್ಷನ್ ಆಫ್ ಎನರ್ಜಿ, ಸೊ ನನ್ನ ಎನರ್ಜಿ ಏನಾಗ್ತದೆ ಅಲ್ಲೇ ಕ್ಯಾಲರಿ ಫಾರ್ಮಲ್ಲಿ ಬರ್ನ್ ಆಗ್ತಿರ್ತದೆ, ಬಟ್ ವರ್ಕ್ ಆಯ್ತು ಅಂತೀರೇನ್ರಿ? ನೋ. Even though I am spending some amount of energy from my body, I can't say the work done on this board, I can't say the work done on this wall, because even though there is a lot of force but there is no displacement. So in such cases we say the work done is 0. And here the third point is about 90 degree. If there is a force as well as a displacement, but the angle between those two is 90 degree, then we say there is no work done. Okay, when you observe such a case, so in our previous topic we have studied the circular motion, and we have studied about the centripetal force. So here this is the path of the circular motion, and say suppose the body is here and its linear displacement is like this, and it is under the action of the centripetal force, right? So if the body is moving in this way, if I take a particular section, its displacement is this much, so the displacement is like this, and the force is here. The angle between these two is 90 degree. So that's why I say the work done by the centripetal force on a body is always 0. There is a force value, there is a displacement value, but the work done is equal to 0 in such a cases. Okay, so it is about the 0 work done. Okay, and also we can get the positive work as well as the negative work. I can explain. We can get the positive as well as the negative. Okay, when do you say the work is positive? Okay, so here the work done may be positive or negative. The work done may be positive or negative, it depending on the direction of the applied force with respect to the displacement, or the direction of net force with respect to the displacement. Okay, so when you can get the positive force, so whenever the force direction and displacement direction are same, so direction of force and displacement are in same direction. Okay, if they are in same direction, the theta becomes 0, then you can get W is equal to F into D into cos of 0. So, you will get FD, which will be the positive. Is it? I can say if the theta is in between, if the theta is in between 0 degree to theta equal to 90 degree, 0 degree to 90 degree, you can get the work done positive, because cos of 0 is 1 and cos of 90 is 0. Okay, so between 90 and 0, so from here to here, so you can get the positive work done. Idar artha enagtada, suppose the body is moving in this way and you are applying a force in the same direction, then we say this is positive work done. If the body is moving here and our applied force is here, it means an angle theta, so it is less than the 90 degree. If I say this like this, it's a 90 now, so the force is acting here like this at a particular angle less than the 90, then also you can get the positive work done. So, this is the condition for positive work done. Okay, and the second case, work done may be negative, when it is negative, if theta is equal to, theta is in between, if the theta is in between 90 degree to 180 degree, suppose the angle between the force and displacement is 180 degree. So, how it is possible to make 180 degree between force and displacement? So, here for the same body, if I applying a force in this direction, okay, I can write it here, okay, and this is the surface and we keep a body on here and I am applying the force, here, as a result there is a displacement, okay, I am applying the force, as a result there is a displacement. Okay, at the same time the body experiences one more opposing force between those two surfaces. What do you call for that force? We call it as, do you know that one? So, that is frictional force, So, now I want to get, was a work done on the body by the frictional force, we take the frictional force in this direction, this is frictional force and here it is displacement. The angle between those two, the friction is here and the displacement is here. So, like this, friction force and this is displacement, the angle between those two is 180 degree. Okay, now the work done will be the negative. So, like this, the work done is the product of the component of force along the direction of the displacement and the displacement. And the SI unit is joule, dimension formula ml square T to the power minus 2, and the work done, that may be positive, that may be negative, that may be 0 also. Okay, this is the basic concept of the work. And for CGS system, we have a unit. In CGS system, unit of work done is that is erg. This is erg. Okay, so in SI system, this is joule and CGS is erg. How to convert the SI system into the erg? Okay, we will see. So, I want to write 1 joule equal to how many ergs? You may get a question. Okay, 1 joule is equal to 1 joule and ಏನಾಗ್ತದೆ ಇಲ್ಲಿ? So, this is, we know W is equal to force into displacement. For the force, I will write MA into displacement. For M, this is kg. For acceleration, meter per second square. For the displacement, this is 1 more meter. Okay, I will write 1 kg meter per second square. 1 joule means. So, now convert these units, these SI units into CGS system. So, 1 kg means 10 to the power 3 gram. 1 meter means 10 to the power 2 centimeter, means 100 centimeter, 1000 gram. How will? So, second square as it is. Okay. So, and I left one more thing here. This is, it's about the force. Okay, and there is one more. This is the meter. Okay, and for 1 meter there will be 2 centimeter. And idellinda bantrida, this is for the force, this is for the displacement. ಇಲ್ಲಿ ಬರ್ದಿದ್ದಲ್ಲ ಅಣ್ಣ, ನಾ ಮರ್ತಿದ್ದೆ ಇಲ್ಲಿ ಬರೆಯೋದಾ. ಓಕೆ, ನೆಕ್ಸ್ಟ್ ಏನಾಗ್ತದ? 10 to the power 3, 10 to the power 2, 10 to the power 1 more 2. ಎಷ್ಟಾಯ್ತಾ? 3 plus 2 5, 5 plus 2 7, 10 to the power 7, 10 to the power 7 gram as it is. Okay, and centimeter and 1 more centimeter, this centimeter square per second square. So gram centimeter square per second. This is called the erg. This is called the erg. So I can write 1 joule is equal to 10 to the power 7 erg. So which is a greater value here? Joule is a greater one. 1 joule equal to 10 to the power 7 erg. So I may get a question. You may get a question like 1 erg equal to how many joules? You can write it like 1 erg is equal to 1 divided by 10 to the power 7 joule. Or you can write 10 to the power minus 7 joule is equal to 1 erg. So these are the conversion factors. So this is important one. 1 joule equal to 10 to the power 7 erg. Okay. And we are discussing about the work done in case of a constant force. In case of a constant force. Why I use the word constant? Because so if you want to apply the formula W equal to force into displacement. Force into displacement. You need to have a constant force. So with a constant force the body is moving. Then you can say the work done is this much. Okay. How to get work done? How to get the work done in variable force? Work done by variable force. By variable force. Work done by variable force. See here is the body. There is a body and it is displaced. It is displaced for 10 meter. It is displaced for 10 meter. If there is a constant force like a 5 Newton was applying, so then you can say there is a 50 joule of work done, 10 into 5. But here once it is 5 Newton, for the next time this becomes 6 Newton, for after 1 second it becomes 7 Newton, for after 1 second it becomes 1 Newton. So like this there is a continuously variation of the force on that body. As a result of the variable force the body is moving. Okay, how to get the value now? Because we know only this much, F into D into cos theta. So if it is not a constant value, how to get the work done here? Should I take the 5 Newton or 6 Newton, 7 Newton or 1 Newton? Okay, in such a cases we have to go through the graphical method. We have to go to the graphical method. So first we should draw a graph of force versus displacement. We should draw a graph of force versus displacement. Force versus displacement. Is it? Okay. So for example, so I can write here 1 Newton, 2 Newton, 3 Newton, 4, 5, 6, 7, 8, 9, 10. Okay. One for a displacement of 2 meter, it was 7 to 8. Next for a next displacement, it becomes 6. Okay, 8. Okay, and like this. So continuously that value is varying. So I draw this much. Like this. See here, the continuously the force is varying. Now this is 5. Okay, for this displacement, so this was 5 to 6. For here to here, it is about 8. For here, it is around 9 to 10. So like this, the value of force is continuously changing and there is a displacement. Okay, so to get the work done in such cases, first we should take a small section. We should take a small section. So that should be very small, such that see this one. So its value I call this A point and this is B point. To displace from A to B, so the force for the A point is around 7. And the 4 point B is very close to the B, very close to the 7. If on A it is 7 Newton and this is 7.1 Newton. Mathematically 7 is not equal to 7.1, it is right. But the effect of force with a 7 Newton is similar like a effect of force at 7.1 Newton. Effect is same, not a number. So then I take so this as a constant now, like a nearly equal. Then I take this force for a small section and I take its displacement A to B, right, and I get its area. Okay, that area itself is a work done for a small displacement dx. Is it? So there is a possibility to integrate all those dw's to get the total work done by the body. So then for the dx with the force F, I can write the dw is equal to that's force and the small displacement dx. Is it? Okay, if I want to get the total work done, there is a method called the integration. So I can write w is equal to integration of all the dw's. Okay, so then you can write integration of force into dx. So this is a one way, but for you the integration is a new thing. So not yet you have studied that integration. So that's why I am trying to go with the easiest way. So how to get this one? How to get this one? Okay, I want to get the area under this curve. I want to get the area under this curve. Area under the curve. Area under the curve. Okay, so this one I take the small section, the same one. So where area under, if I take the rectangle, ಈ rectangle ಅಷ್ಟೇ ನಾ ತಗೊಂಡ ಇದ್ರ area find ಮಾಡಬೇಕಾ. So area of rectangle, area of that small rectangle, area of that small rectangle. So ಏನಾಗ್ತದೆ ರೀ, it is the length and this is the breadth. What that length indicate? Length is along y axis, so that is force. So I can write length into breadth. So for the length this is force, and for the breadth this is the displacement dx. Okay, force into displacement. So this is called the small work done. This is called the small work done. I call this is w. Okay, and this is the f. Okay, dw. Sorry, dw. So this is the work done in such a small displacement. Is it? I want to get the total work done. Take a one more section and call it as a dx. Get its work done, and take a one more small section and get its work done. Take one more small section and get its work done. Okay, and add all the work done. Add all the dw's, you will get the total work done. Or in other way, I can say area under the entire curve. So if I take the small sections, if I take a small section, what happens? It covers the entire area under that curve. Curve ಕೆಳಗಡೆ ಇರೋ ಎಲ್ಲ ಏರಿಯಾನು ಅದು ಕವರ್ ಮಾಡ್ತದೆ ರೀ. ಅವು ನಾ ಏನಂತ ಹೇಳ್ತೇನಾ. ಸೊ therefore area under the force displacement curve, area under the force displacement curve is equal to, I can say this is the total work done in that journey, total work done for that entire displacement. So this is a way to get the work done in case of variable force. Okay, so next point is energy. Okay, so energy, how to define the energy? See how much we can work. ನಾವು ಎಷ್ಟೊತ್ತು ನಾವು ಕೆಲಸ ಮಾಡ್ಬೋದು, ನಮ್ಮ ಒಳಗಡೆ ಎಷ್ಟೆಷ್ಟು ಎನರ್ಜಿ ಇರ್ತದೋ ಅಷ್ಟೊತ್ತು ನಾವು ಕೆಲಸ ಮಾಡ್ತಿರ್ತೇವೆ. ಸೊ ಯಾವುದೋ ಒಂದು ಮಷಿನ್ ಅದ ರೀ ಅಥವಾ ವೆಹಿಕಲ್ ಮಷಿನ್ ಅದ, ಅದನ್ನ ನಾವು ಚಾರ್ಜ್ ಮಾಡ್ತೇವೆ. ಒಂದು ಮಷಿನ್ ಅದ ರೀ ಲೈಕ್ ಎಲೆಕ್ಟ್ರಿಕಲ್ ವೆಹಿಕಲ್ ಅದ, ಅದನ್ನ ಚಾರ್ಜ್ ಮಾಡ್ತೇನೆ. ಅಲ್ಲೇನಾಗ್ತದೆ ರೀ, ಇಟ್ ಟೇಕ್ಸ್ ದ ಎಲೆಕ್ಟ್ರಿಕ್ ಎನರ್ಜಿ, ರೈಟ್. ಸೊ ಆಮೇಲೆ ಅದು ಎಲ್ಲಿ ತನಕ ಕೆಲಸ ಮಾಡ್ತದ, ಎಲ್ಲಿ ತನಕ ಅದು ಓಡ್ತದೆ ರೀ ಎಲೆಕ್ಟ್ರಿಕ್ ವೆಹಿಕಲ್, ಅಂಟಿಲ್ ಆಲ್ ದ ಚಾರ್ಜ್ ಡಿಸ್ಚಾರ್ಜ್ಡ್. ಅದರೊಳಗಿರೋ ಎಲ್ಲ ಚಾರ್ಜ್ನೂ ಖುಲ್ಲ ಆಗಬೇಕಾ, ಅಲ್ಲಿ ತನಕ ಏನಾಗ್ತದ ಅದು ಕೆಲಸ ಮಾಡ್ತಾನೆ ಇರ್ತದ, ಹೌದಿಲ್ಲ ರೀ. ಓಕೆ, ಸೊ ಎಷ್ಟು ಕೆಲಸ ಮಾಡ್ತು, ಅದ್ರೊಳಗೆ ಎಷ್ಟು ಎನರ್ಜಿ ಸ್ಟೋರ್ ಇತ್ತಲ್ಲ ಅಷ್ಟು ಕೆಲಸ ಮಾಡ್ತು. ಎಷ್ಟು ಕೆಲಸ ಮಾಡಬೇಕದು, ಎನರ್ಜಿ ಎಷ್ಟದನೋ ಅಷ್ಟು ಕೆಲಸ ಮಾಡು. ಮೀನ್ಸ್ ಎನರ್ಜಿ ಆ್ಯಂಡ್ ವರ್ಕ್ ಡನ್, ದೇ ಆರ್ ರಿಲೇಟೆಡ್. See, the numerical values of energy are equal to the work done. ಎಷ್ಟು ಎನರ್ಜಿ ಐತಪ್ಪ, ಎಷ್ಟು ವರ್ಕ್ ಡನ್ ಆಗ್ತದೆ ನೋಡೋಣ, ಅಷ್ಟು ಎನರ್ಜಿ ಇರ್ತದೆ. ಎಷ್ಟು ವರ್ಕ್ ಆಯಿತು, ಎಷ್ಟು ಎನರ್ಜಿ ಸ್ಟೋರ್ ಇತ್ತು, ಅಷ್ಟು ವರ್ಕ್ ಡನ್ ಆಯಿತು. ಸೊ ಎನರ್ಜಿ ಆ್ಯಂಡ್ ವರ್ಕ್ ಡನ್, ಸೊ ದೇ ಹ್ಯಾವ್ ಸೇಮ್ ನ್ಯೂಮರಿಕಲ್ ವ್ಯಾಲ್ಯೂ and they also have a same SI unit as well as a same dimensional formula. Is it? Okay, then how to define the energy? So it is, energy is the capacity of doing work, the capacity of doing work. So this is called the energy. So you may have seen, you may have observed the many types of energy, like heat energy, okay, and mechanical energy, electrical energy, magnetic energy, light energy. Okay, so there are so many energies. Okay, for all the energies the SI unit is same, that is joule, and the dimension formula is same, ml square t to the power minus 2. Okay, for all the form of energy the SI unit, dimension formula, so are same. And in our topic we have restricted for the mechanical energy only. We are restricted for mechanical energy only. So how to define the mechanical energy? How do you say what's the mechanical energy? Mechanical energy is a sum of kinetic energy and potential energy. is a sum means plus, sum of kinetic energy and potential energy. This is called mechanical energy. Then there are two new things. So what is the kinetic energy? What is the kinetic energy? Kinetic energy. So this is the energy associated by the body by virtue of its motion. The energy associated by the body by virtue of its motion. ಯಾವುದಾದ್ರೂ ಒಂದು ವಸ್ತು ಮೂವ್ ಆಗ್ಲಾತಿತ್ತ, ಆ ಮೋಷನಲ್ಲಿದ್ದಾಗ ಅದರಲ್ಲಿರೋ ಎನರ್ಜಿಗೆ ನಾವೇನಂತ ಕರಿತೇವೆ ರೀ, ನಾವು ಅದ್ರ ಜೊತೆ ಇರೋ ಎನರ್ಜಿಗೆ ಏನಂತ ಕರಿತೇವ, ಕೈನೆಟಿಕ್ ಎನರ್ಜಿ. ಆ್ಯಂಡ್ ಇಟ್ಸ್ ಫಾರ್ಮುಲಾ ಈಸ್ kinetic energy is equal to half mass of that moving body and speed of that moving body square, half mv square. This is the dimension formula for kinetic energy. Was a SI unit. I already told you, for any form of energy the unit is same. That may be kinetic energy, that may be potential energy, that may be total energy, that may be heat, that may be electric, that may be magnetic, anything. For all the energies the unit is joule. Okay, and the next one more form, this is the potential energy. It is potential energy. So what's the potential energy? The energy associated with the body, by virtue of its position, So this is called the potential energy. And you may get a question, how it can have energy even though it is at rest? Okay, for example, so we may have seen the water reservoir like a water dam. Okay, ನಾವು ಡ್ಯಾಮ್ ನೋಡಿರ್ತೀವಿ ರೀ. ಓಕೆ, ಆ ಥರ ಒಂದು ಡ್ಯಾಮಲ್ಲಿ ಏನಾಗಿರ್ತದ, ಸೊ ಒಂದು ಕಡೆ ಎಲ್ಲ ನೀರನ್ನ ಸಂಗ್ರಹ ಮಾಡಿರ್ತಾರೆ, ಒಂದು ಕಡೆ ಏನಿರ್ತದ ಓಪನಿಂಗ್ಸ್ ಇರ್ತಾವೆ, ನಾವು ಅದಕ್ಕೆ ಏನಂತೇವೆ ಡ್ಯಾಮ್ ಗೇಟ್ ಅಂತೇವೆ. ಹೌದಾ? ಸೊ ನೀವೇನಾದರೂ ಡ್ಯಾಮ್ ಗೇಟ್ ಓಪನ್ ಮಾಡಿದ್ರಾ, ಮೊದಲು ಡ್ಯಾಮ್ ಗೇಟ್ ಎಲ್ಲ ಕ್ಲೋಸ್ ಇತ್ತು, ಎಲ್ಲ ನೀರಿಂಗೆ ನಿಂತಿರ್ತದೆ ಹಿಂಗೆ. ಓಕೆ, ಸೊ ನೀವು ಏನಾದರೂ ಡೋರ್ಗೆ ಓಪನ್ ಮಾಡಿದ್ರಿ, ಆ ಗೇಟ್ ಓಪನ್ ಮಾಡಿದ್ರಿ, ವಾಟರ್ ಏನಾಗ್ತದ, ಹರಿಲಾಕ್ ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತದ, ಫ್ಲೋ ಆಗ್ಲಾಕ್ ಚಾಲು ಮಾಡ್ತದ. Means that substance comes to the motion. So when it is in a motion, there must be the kinetic energy. Because of that energy it is moving. And see, so as per the conservation of energy, as per the conservation of energy can neither be created nor be destroyed. It means gate open ಮಾಡಂತಲೇ ಎನರ್ಜಿ ತಾನಾಗಿ ಕ್ರಿಯೇಟ್ ಆಯ್ತೇನಲ್ಲೇ? ನೋ, ಕ್ರಿಯೇಟ್ ಆಗಿಲ್ಲ. ಇನಿಷಿಯಲಿ ಇಟ್ ವಾಸ್ ಹ್ಯಾವಿಂಗ್ ಸಮ್ ಅಮೌಂಟ್ ಆಫ್ ಎನರ್ಜಿ, ದಟ್ ವಾಸ್ ಸ್ಟೋರ್ಡ್ ಎನರ್ಜಿ. Okay, that stored energy is converted into kinetic energy. So that stored energy I call the potential energy. I call it as a potential energy. Okay, so by virtue of its position, for example, I am having a body here at a particular height. See here, now that body is at rest, and still I say it is having some amount of energy. How do you say? So remove its support, it start to move. And how it start to move? Because of the gravitational force. Okay, and if it started to move, then I say it is having kinetic energy. How it got the kinetic energy? Initially it is having some stored energy as a potential, so now it is changed into a kinetic. So if having one body here and next time here, okay, so both the bodies, are they having the same potential energy? No, its position is different and its position is different. So with respect to the position, the energy is defining. So here its energy is more than this one. How do you get this confirmation? So if you leave this body, it will reach the earth with a more speed. It will reach with the earth with a less speed. Okay, so then 1/2 mv square differs, the kinetic energy differs, so that's the stored energy was different. So this is about the potential energy. And what's the formula for potential energy? Potential energy is equal to m into g into h. So here mg into, for example, it is at 10 meter, its weight is mg into 10 meter. If I keep the same body here, mg is same but height increased like a 12 meter. So it was mg into 10, here it is mg into 12. So it's a potential increase. I keep it here, so this become 15 meter. Okay, mg as it is, but the height is varying. As height varies, the potential energy of that body increases. with respect to the height of the position of that body. Okay, so this is about the potential energy, kinetic energy and the total energy.